Good morning, friends. Once again, I welcome you all for series of lectures on microprocessors and microcontrollers. In this class, I'm going to discuss about a concept called interrupts in 8086. First, what is meant by an interrupt? Basically, an interrupt is a disturbance signal from processor point of view. At the same time, it is a request signal from the device who generate this interrupt signal. So this interrupt signal we can see from both ends. One end, that is from processor end, absolutely no doubt, it is a disturbance signal. Once this signal comes to the processor, it breaks whatever the task it was doing at the time, or it disturbs what is the task that time it was doing. So it is a disturbance signal from processor point of view. At the same time, it is a request signal from the device actually who generate this signal. So that this interrupt we can call as interrupt request signal. See here, friends, our processor executing this main program. At this junction, it receives an interrupt from IO device end. What it do is it stop execution here and it shift execution to some other program. This program is known as interrupt service routine, ISR. Once it completes the execution of interrupt service routine, that means by execution of its last instruction, that is IRET, means a return from interrupt service routine. Again, we come back to the previous stopped program and we continue the execution of the program. So here what we can say is, if the processor is willing to provide a service for an interrupt, it stops the execution of the interrupt at that point where it was receiving an interrupt, and it shift execution to an interrupt service routine. That means it shift the execution to some other program. That program is known as interrupt service routine. After successful execution of the interrupt service routine, how we can identify that it successfully complete the execution of interrupt service routine is by execution of its last instruction, that is I return. In some other processor, the instruction may be RETI, which indicates return from interrupt service routine. Once it will execute that instruction, it return to previous stopped program. There are different types of interrupts. Here I mentioned some of the interrupts. These types of interrupts we observe when we are learning about the different microprocessors and different controllers. The first type of interrupts are hardware/software interrupts. The second variety of interrupts are maskable/non-maskable interrupt. The third type is vectored/non-vectored interrupts. Fourth type is edge/level triggered interrupts. And fifth type is internal/external interrupts. Like this, there are different types of interrupts supported by our processors as well as controllers. We should know what is this hardware interrupt, what is software interrupt, what is maskable, what is non-maskable, like this. I just to give a brief idea regarding to what about these interrupts. The first one is hardware interrupt. The interrupt signals are basically generated by hardware circuits. Such interrupts we can call as hardware interrupts. The hardware devices, in the sense, in our system, we have different IO devices, memory elements, along with a processor. The memories can't generate any interrupts, but the interrupt signals are generated by IO devices. Basically, those are the requests from IO device, and the same signals can be treated as interrupts from the processor end. So here hardware interrupts means the interrupt signals are generated by hardware devices, nothing but IO devices. The second variety is software interrupts. Basically, these interrupts are generated by execution of some dedicated instructions. These instructions are changing from processor to processor. In case of 8086, the interrupts can be generated by execution of an instruction called INT, where n is equal to 0, 0 to 255, because our 8086 will support 256 interrupts. Here, software interrupt means an interrupt can be generated by execution of some dedicated instruction. The next type is maskable / non-maskable interrupts. In that, what is this maskable interrupt means? If you want to call an interrupt is a maskable, the processor have a choice. The processor may postpone the services or completely neglected the services. Such interrupts we can consider as maskable interrupts. That means from processor point of these interrupts not having that much highest priority. Because of that reason only, the processor may postpone the services or completely neglected the services. But the second category of interrupts are non-maskable interrupts. If you want to call an interrupt is non-maskable, for that interrupt, the processor must provide the service without any delay because your processor gave highest priority to these non-maskable interrupts. The best example for non-maskable interrupt is power failure interrupts. Once a power failure comes, that information is carried by our power supply subsystem to our processor. That request immediately our processor should respond because that is a non-maskable. The best example for non-maskable is power failure routes. The next type is vectored / non-vectored interrupts. If you want to call an interrupt is vectored, means the processor itself is automatically calculates the service routine address. It didn't depends on the interrupting device where your service routine is. Your processor itself can calculate a service routine address automatically. Such interrupts we consider as vectored interrupts. The second type is non-vectored interrupts. If you want to call an interrupt is non-vectored, the processor is unable to calculate a service routine address, that is ISR address, automatically. It depends on interrupting device for ISR address in order to provide a service for that interrupt. And the next category is edge / level triggered interrupt. If you want to call an interrupt is edge triggered, that means the processor can accept the interrupt signals from the external devices which are coming through and interrupt signals only at either leading edge or falling edges of the clock signal. Because we know that our processor is synchronous device. If you want to do any task without our processor, in that task, different signals are used, different devices are participating. Those signals activation and deactivation and the devices activation and deactivation follows definitely a reference signal called a clock. Here also, some interrupts can be received or accepted by the processor with reference to the clock. If the reference signal is the edges of the clock, such interrupts we can consider as edge triggered interrupts. Next one is the level triggered interrupts. That means the processor can accept these interrupt signals from the external devices through interrupt signals only either at positive level or negative level of the clock. Like this, we have another classification. And one more classification is our interrupts are internal or external. If you want to say an interrupt is an internal, the interrupt signals or generation was done internal to the processor. That is inside of the processor. If an interrupt was generated inside of the processor, such interrupts we consider as internal interrupts. If the interrupt generation is done outside of the processor, that is external to the processor, such interrupts we consider as external interrupts. Like this, we have a different varieties of interrupts. Now coming to 8086 interrupts. Our 8086 processor will support total 256 interrupts. All interrupts are the vectored interrupts. We know what is the meaning of vectored interrupts. And one more thing is, for all these vectored interrupts, the vector addresses, that is ISR addresses, are available in an interrupt vector table IVT. In this IVT, each and every interrupt we assigned 4 locations. 2 locations provides offset address, that is a IP value, and 2 more locations will provide the base address of ISR, that is CS value. We know that how we are calculating a physical address in architecture part. The summer circuit always will produce a 20-bit physical address by using a basic formula, that is physical address is equal to base address into 10H plus offset address or effective address. In order to shift our execution from current execution point to interrupt service routine, we should calculate the first instruction physical address in ISR. That physical address, how we are calculating? We are calculating by the combination of base address as well as offset address. So for each and every interrupt, we dedicate a 4 locations in interrupt vector table IVT. Then what should be the size of IVT? No doubt it is equal to 1024 bytes, because we know that the total interrupt supported by the processor is 256. And for each interrupt, we dedicate a 4 locations. So that 256 into 4, it is equal to 1024. This is the size of our IVT. Where it was? It was stored in the first 1 kilobyte of 8086 addressable memory of 1 MB. We know that our 8086 will support 1 MB of memory. In that first 1 kilobyte of memory was dedicated for interrupt vector table IVT. And one more thing, here our 8086 will support two hardware interrupts. One is NMI and second one is INTR. By using NMI and INTR only, our processor can receive hardware interrupts from IO devices. At the same time, it also supports 256 software interrupts. We know that how the software interrupt can be generated. The software interrupts in case of 8086 was generated by execution of a dedicated instruction called INTN, where N value is from 0 to 255 or in hexadecimal 00H2 0FFH. So this is an interrupt response. So what exactly our processor has to do? It wants to provide a service for the received request. See here, friends, what our 8086 can do. This is the program execution right now our processor was doing. At this junction, it receives an interrupt and it is willing to provide a service for it. Before shifting our execution to interrupt service routine, it has to do few things. Why it has to do these few things? In order to avoid the problem after completion of execution of this service routine, once again we come back to our previous stopped program. That time we didn't face any problem. That is only possible before shifting our execution from here to here. We should do all these things. In that, what we do? The first we pushes the flags value. At this point, your program have certain status. That status information can be provided by flags. That flags information first we push it onto the stack. Later, we should clear interrupt flag IF as well as we should clear trap flag TF. Once we clear interrupt flag IF, that means our processor is not willing to accept any new interrupt which is coming from IO device and through INTR, because interrupt flag IF becomes 0. And one more thing is we are clearing TF. The reason for this is once we are not clearing TF, our processor is entering into single step execution mode. That means for each and every instruction execution, it will provide a result to us. If it is okay, it will go and execute a second instruction. It is a time-taking process. To avoid these two things, first I should clear interrupt flag IF and later I should clear trap flag TF. And thereafter, the current executing next instruction address. Because after completion of interrupt service routine, again we come back to previous stopped program. For that case, we should know the address of where we stopped our previous program. For that, we push the CS value, we push IP value at the time. Later, we have to calculate ISR address by using IVT. Then we can copy that value into CS and IP. Then we shift our execution from this interrupt service main program to interrupt service routine. Before starting execution of that, it will do one more thing. That is, it pushes different register values in the stack. Because up to this, we are using different registers of processor and they maintain different values. Once we start execution of your interrupt service routine, there is a possibility that the same register you may go and use. At the end of this interrupt service routine, those registers may not have the same values what we have previously in this program execution. To avoid that difficulty, what I was doing is before starting execution of this interrupt service routine, I push some of the register values in the stack. Then I start execution of interrupt service routine. When it comes to an end, again, what are the register values I pushed previously in the stack? The same register value I retrieved back by execution of an instruction called pop registers. Then I was executing iReturn. Then I come back to previous stopped program. In that process, what I have to do is first I retrieve a IP value. Later, I retrieve a CS value. And then I retrieve flags values. These are the register values previously we stored in the stack. In a reverse adder, these values we retrieve from the stack because we know that the operating principle of stack is last in first out. At the last, I was pushed IP value so that I was first to retrieve IP value from the stack. Before that, I push a CS value. Later, I pop the CS value. At the beginning, I was pushed the flags value. At the end, I pop the flag values. Like this, our processor will provide a services for interrupts. The same thing here, I mentioned step by step. It decrements the stack pointer SP value by 2 and pushes the flag register value onto the stack. That is the push flag registers. Next is disable 8086 INTR interrupt input by clearing interrupt flag IF. And it resets trap flag, that is a TF. If you are not doing that, no doubt our processor is entered to single step execution mode. To avoid it, we should clear trap flag also. So ISR is not executed in single stepping mode. Next, a decrement the stack pointer value by 2 to push a CS value, that is a code segment register value onto the stack. At the end, we push the IP value. Before that, again, we stack pointer content should be decremented by 2. It will provide a new allocations in the stack. Later, we have to calculate a service routine address with the help of IVT. Then we jump to interrupt service routine IOC. So like this, a sequence of steps or 8086 should follow. Next, we'll go on through 8086. We know that it will support a 256 interrupts. Those 256 interrupts are basically divided into 3 groups. The first group of interrupts are called dedicated interrupts. These are 5 in count. Those are from type 0 to type 4. The second group of interrupts are reserved interrupts. These are 27. These are from type number 5 to type number 31. The last category is user-defined interrupts. These are remaining 224 interrupts. These are from type number 32 to type number 255. Now we'll learn a little bit regarding to these categories. The first one is the dedicated interrupts. For these interrupts, service routines are basically defined or written by the manufacturer. Because of that reason, these dedicated interrupts we can also call manufacturer defined interrupts. That means for these interrupt service routines are defined by the manufacturer. That's why these are called a default interrupts or dedicated interrupts or manufacturer defined interrupts. These are 5 in count. The second one is reserved interrupts. These interrupts are reserved by the Intel for their future designed processors. In future design processor, you may identify that some more dedicated interrupts. For those interrupts also, service routines may be written by the manufacturer. Because of that reason, the Intel people reserved 27 interrupts in 8086 for future design processors in same 16-bit processors category. After 8086, from 80186 and 80286, another 2 more 16-bit processors was launched by our Intel. In those processors, some of these interrupts are used under these reserved interrupts. Those are becomes a dedicated interrupts. That means some of the reserved interrupts are defined in 80186. Some more interrupts are defined in 80286 under these reserved interrupts. These are becoming as a dedicated interrupts. And last category is user-defined interrupts. For these interrupts, the service routines are defined or written by the user. According to user wish, the user may define these are 224 interrupts. So once you're observing this entire picture, some of the interrupts are defined by the manufacturer, and some of the interrupts are defined by the user, and some of the interrupts are reserved by Intel for future design processors for them. Now we learn about a dedicated interrupts. Basically, these are 5 interrupts we have, that is a type 0 to a type 4. We are going to learn a little bit about this type 0 to type 4, one after other. The first one is a type 0 interrupt. It is, we can also call divide by 0 interrupt. Basically, this type 0 interrupt was generated whenever the processor executes a division instruction with unfortunately divisor value is equal to 0. We know that we divide something with 0. Obviously, the result is infinite. So here that was happened in terms of an interrupt. Basically, this interrupt can be generated when the processor executes the division instruction with a divisor value equal to 0. This is the one way how this type 0 interrupt was generated. Another way is this interrupt also can generate by execution of an instruction called INT00H. You know that The interrupts also generated with the help of software instructions. For our 8086 case, we are using an instruction is INT. So that this type 0 interrupt we can generate by execution of an instruction called INT00H. And we know that for each and every interrupt, what our 8086 will support, all are the vectored interrupts. That means the ISR addresses for all these interrupts are available in interrupt vector table. Then we should calculate what is the starting address in that IVT to get ISR address of corresponding interrupt. That address we are calling as vector address. That vector address we are calculating just by doing a simple mathematical equation, that is a type number is multiplied with a 4. Then we may get a vector address of IVT for the corresponding interrupt. That is the starting location in IVT. From that onwards, we are accessing 4 locations. We may get a IP value as well as CS value of interrupt service routine. And one more interesting thing regarding to this divide by 0 interrupt, that is a type 0 interrupt, is it is an exception of 8086. What is the meaning of exception? Basically, exception means it is a runtime error. No one can do the operation division with the divisor value 0. It may happen, unfortunately. So that's why it is considered as a runtime error. So exception of 8086 is nothing but type 0 interrupt. Type 0 interrupt we can consider as exception of 8086. Exception means it is a runtime error. And the second dedicated interrupt is a type 1. It is called single step execution interrupt. This interrupt was generated whenever the trap flag TF becomes 1. That is, trap flag is set. This is one way for generation of this interrupt. We can also generate this interrupt by execution of an instruction called INT01H. And obviously, the vector address in IVT for this interrupt is 004H. Again, how we are getting this? Yes, we are doing a multiplication, type number with a 4. Here, type number is 1. 1 into 4, that is equal to 004H. That's a simple logic. The next one is type 2 interrupt, which is called non-maskable interrupt. This interrupt was generated whenever the processor receives an interrupt from external devices by using NMI signal. NMI means non-maskable interrupt. The same interrupt can also be generated by execution of an instruction called INT02H. And for this interrupt, vector address in IVT is equal to 0008H. The fourth one is a type 3 interrupt. Basically, it is called breakpoint interrupt. This interrupt was generated only one way, that is by execution of an instruction called INT03H. And one more thing is the specialty of INT03H is basically we use this instruction as a terminating instruction in our 8086 assembly language programs. And this interrupt along with the type 1 interrupts, these two are very, very useful for us in our debugging process. Debugging means checking of errors. In debugging process, we ultimately use two interrupts. One is a type 1 interrupt, which is our single step execution interrupt, and second one is a type 3 interrupt, which is called breakpoint interrupt. For this interrupt, vector address in IVT is equal to 000CH. And coming to the last, that is a type 4 interrupt, which we are calling as overflow interrupt. This interrupt was generated whenever the overflow flag is set, that is OV or OF is equal to 1. It can also generate by execution of an instructions. One is INT04H and another one is INTO. INTO means interrupt on overflow. For this interrupt, the vector address is equal to 0010H. Like this, there are 5 dedicated interrupts. For these 5 interrupt service routines are defined by the user manufacturer. Because of that, these are called manufacturer defined interrupts. Now we will see interrupt vector table IVT. See here, friends. This is our interrupt vector table. So starting address is 000H and last address is 3FFH. It is equal to 1023. We start from a 0 and we end at 1023. That is a decimal equivalent for 3FFH. Then the total size of this IVT is equal to 1024 bytes, which is nothing but it is 1 KB. See here, friends, for each interrupt, we are dedicating 4 locations. So from 000 to 004, this is 004 is starting address for the next single step execution interrupt. So divide by zero interrupt, we are allocating 4 locations, that is a 000, 001, 0, 002, and 003. Out of these 4 locations, 2 locations we're dedicating for offset address, which is an IP value of our service routine, and 2 more locations we're dedicating for CS value, which is the base address of our interrupt service routine. See here, friends, 5 interrupts we consider as a dedicated interrupts. That is a type 0 to type 4. Later, type 5 to type 31 we consider as reserved interrupts. Their count is 27. And later, type number 32 to type number 255. These are 224 interrupts we consider as user-defined interrupts. For all these interrupts, vector addresses are this. In these vector addresses, we have these are the service routine addresses. Like this, we are using interrupt vector table in case of our 8086. I hope you understand what an interrupt is, what are the different types of interrupts, and what are the 8086 interrupts. In that, what are the different types, how we are calculating service routine address, IVT, everything you understood. Thank you for patient listening. In the next class, once again, we'll discuss one more topic. Thank you for patient listening.